So section 7.2 is really short. It's only like a page in your textbook, but it just talks about how things in general get across a cell membrane. And so it starts off by saying that cells must exchange things from the inside of the cell to the outside of the cell. We've been saying that this whole time. If we can't get things across the cell membrane, then there's no way to get wastes out and things we need in. So it's really important that these cell membranes can transport things across the cell membrane. But we only want to let the bad things out and we only want to let the good things in, right? Or the things that we want out. And we need to maintain that balance somehow. Otherwise, our cell's going to self-destruct if it can't get if it lets everything in, including bad things, and if it lets out all the things that we want to keep. So it's really important that our cells are selectively permeable. Selectively, again, meaning it chooses, and permeable meaning things crossing. So permeable, things can come in, things can go, but only based on what the cell says. So it's pretty easy to get hydrophobic substances just across the cell membrane if they're relatively small, because they can pass through the phospholipid bilayer. Remember, the phospholipid bilayer is composed of hydrophilic heads on the outside and hydrophobic tails in the middle with proteins stuck in the middle. But if something's hydrophobic, it can pass right through the phospholipid bilayer. So that's really important. They can just cross it on their own. However, polar molecules like sugar, water, or ions especially, ions have a full charge. There's almost no chance they're getting across because it's so hydrophobic. Wait, let's look at a picture. I don't have a picture anymore. Sorry, flipping back to 7.1. Okay, so here's our cell membrane. Whichever one of these you want to look at. Let's say the top is the outside of the cell and the bottom is the inside of the cell. They have to cross through this hydrophobic area. So non-polar molecules can do that just fine. They can just diffuse right across. Some example of non-polar substances are hydrocarbons, so big long chains of hydrocarbons. Carbon dioxide is nonpolar. Oxygen is nonpolar, O2. So those can cross on their own whenever they feel like it, right through the cell membrane. However, these guys are so nonpolar that anything that has a slight charge on it, meaning water has a slight charge on it because the oxygen is a little bit more negative than the hydrogens. Glucose is the same way. And any ions like salt, NaCl, with the positive Na and the negative Cl, is not crossing this. With its full charge, there's no way it's getting across. So we have these things called transport proteins. If you think back to the proteins that are stored in the cell membrane, there were ones that were specifically used for transport. So they can form channels in the cell membrane that allow these polar molecules and ions to cross, because the amino acids that will be facing the inside of the channel will be polar. Their R groups will be polar or charged, so it's not a problem for them to pass through. Channel proteins that facilitate the passage of water we call aquaporins. It's easy to remember this because aqua means water and porins are like little pores in the cell membrane that allow water through. Those are really important. Water can pass through an aquaporin, let me give you this, at a rate of 3 billion water molecules a second in a single file line. 3 billion water molecules a second. If we didn't have aquaporins and they had to diffuse through the hydrophobic cell membrane, it would not work nearly as quickly. I mean, it's hard to beat 3 billion water molecules a second, but it wouldn't even come close. So it's really important that we have these proteins that allow for transport across the cell membrane. Then we also have these things called carrier proteins, which we're going to discuss in more detail, but they kind of pick up what they want, change their shape, and bring it inside. And transport proteins are very specific for the substance that they're moving. It's kind of like how enzymes and substrates have such specificity, so do carrier proteins and what they're carrying. Because if they're going to pick up anything and bring it inside the cell membrane, it's still not doing its job. We want it to be selective. So a glucose carrier is only going to pick up glucose, and it's not going to pick up fructose or sucrose or anything bad for the cell either. If there's bacterial invasion in your cell, it's not going to grab a bacteria and pull it inside, or at least that's not what its job is to do. So it's very important that carriers have specificity as well.